Okay, so strong electrolytes. Remember, a strong electrolyte is something that separates into ions when dissolved in water. Strong electrolytes are going to have a bigger effect on the colligative properties because they give more particles, right? So in theory, sodium chloride, having a sodium ion and a chloride ion, when you dissolve 1 mole of that, you should get 1 mole of sodium ions and 1 mole of chloride ions, which gives you 2 moles of particles instead of 1, right? Of course, it's not always perfect. So we have a factor that compensates for that. The Van 't Hoff factor is given the symbol I, not to be mistaken for imaginary numbers. It's the ratio of moles of particles in solution to moles of formula units dissolved. And they're not, the actual ones are not always exactly what we expect because some ions effectively pair up in solution. And when they're paired like that, then they kind of act like 1 particle instead of 2. But we can calculate an ideal Van 't Hoff factor by looking at the formula for the ionic compound. It's the moles of particles, so total number of cations and anions, divided by the moles of formula units. So if we look at sodium chloride has 2 ions in it, right? One positive cation and 1 negative anion. So we expect a Van 't Hoff factor of 2 moles of ions per mole of sodium chloride. So that's the expected. The measured is 1.9. It's close, but not exactly. Magnesium sulfate. So there's a magnesium ion and a sulfate ion. We expect a Van 't Hoff factor of 2, but this does more pairing, and so it's actually only 1.3. You do not need to know the measured Van 't Hoff factors. Magnesium chloride, we would expect 3, because 1 magnesium and 2 chlorines for every 1 mole of the compound. Does that make sense? It's number of ions. This is what happens with ion pairing. So the chloride ion is surrounded by water molecules. It's got its ion dipole forces going on there, and the sodium ion has its ion dipole forces going on, and yet there's still some sort of attraction between them. And so even though they're surrounded with water molecules, they're still going to hang out together. We don't need to understand that, but we just need to be okay with it. Sometimes you just have to say, I'll believe you. I really don't want you to explain exactly why that is. No, we're good. We're good. We'll just go with that. So when we have an ionic solution, something with a strong electrolyte, then we have to use the Van 't Hoff factor because it will multiply and make the freezing point depression lower, the boiling point elevation higher, and it will make the osmotic pressure higher as well. So it's the same formulas. It was delta TF equals M times the constant. We just multiply by that I factor for each of these. Any questions? You would get the I factor. The question may say, assume an ideal Van 't Hoff factor. Then you look at the chemical formula and figure out how many ions are in 1 formula unit of that. That's the Van 't Hoff factor. Or it may give you an actual Van 't Hoff factor, and then you just stick it in there. Those factors don't have units. So let's do an example. Calculate the freezing point of an aqueous 0.1 molal iron 3 chloride solution using a Van 't Hoff factor of 3.2. So freezing point, we're going to calculate freezing point depression. So the change in temperature of the freezing point is the Van 't Hoff factor times the molality times the freezing point depression constant for water. It's for the solvent. Aqueous is water. So we're given the Van 't Hoff factor. So it's 3.2, no units. We're given the molality, 0.10 molal. And then we need the freezing point depression constant. You'd go look it up in the table. Don't expect you to memorize that. Since we just did one, I've got it in my head. It's 1.86 degrees Celsius per molal. So we've got 3.2 times 0.1 times 1.86. Zero 0.5952. Yeah. Degrees Celsius, 2 sig figs. So what's the freezing point? Negative. Freezing point of pure water is 0, so it's 0 degrees Celsius minus that number. So the freezing point is negative 0.59 degrees Celsius. Any questions? Yes, thank you. Yeah, because the next digit's a 5. There we go. Thanks. So strong electrolytes also are going to have a larger effect on the vapor pressure lowering. So we have to account for the dissociation of the solute when we're calculating the mole fraction. So the vapor pressure was calculated using the mole fraction of the solvent and the solute, and so we need to think about that when we calculate the mole fraction. So here's an example. A solution contains 0.115 moles of water and an unknown number of moles of sodium chloride. The vapor pressure of the solution at 30 degrees Celsius is 25.7 torr. The vapor pressure of pure water at 30 degrees Celsius is 31.8 torr. Calculate the number of moles of sodium chloride in the solution. Well, we need to remember the equation relating the vapor pressure. So the pressure of the solution, the vapor pressure of the solution, is going to equal the mole fraction of the solvent, so that's water here, times the vapor pressure of the pure solvent. Sodium chloride is not a volatile solute, and so we don't have to worry about it adding to the vapor pressure, because it won't do that. So we know what the vapor pressure of the pure water is, and we know what the vapor pressure of the solution is, so we can calculate the mole fraction of water. So the mole fraction of water is going to equal the vapor pressure of the solution divided by the vapor pressure of the pure solvent. So the solution is 25.7 torr. The pure solvent is 31.8 torr. The torrs cancel out. 25.7. Oops. Zero 0.808. No units. That's the mole fraction. Well, we want the moles of sodium chloride. So this mole fraction of water equals the moles of water divided by the moles of water plus the moles of sodium chloride. Right? Well, we know what the moles of water are, 0.115. So we could substitute that in. So this is going to equal 0.115 moles over 0.115 moles plus the moles of sodium chloride. This is where we have to be a little bit careful. Moles of sodium chloride, 1 mole of sodium chloride would give us how many moles of ions? 2. So this number that we're calculating here, this number is actually the moles of ions, not the moles of sodium chloride. So we think about that and we're like, oh, let's be careful. Let's remember what we're really... So it's the moles of ions. And we'll change this one over here as well. So now we have to do a little bit of algebra. So we're going to get 0.80818. So that's this guy up here. I'm cross-multiplying. I'm going to multiply by this quantity. So times 0.115 moles plus number of moles of ions is going to be equal to 0.115 moles. And then you distribute. So you've got the 0.80818 times 0.115. Plus 0.08, no, not 0.8, 80818 times the number of moles of ions is equal to 0.115 moles. Wow, that's really messy. Yeah. So then we've got this moles and those moles, and so we're going to take 0.115 minus this. 0.115 minus 0.09294. We're going to get 808.18 is equal to 0.02206 moles. And then we've got to divide both sides. Number of moles of ions equals, oh, I stuck that 0 in there again. There's no 0 there. .0272996 moles. Anybody else doing the math with me? Okay, is that right so far? Okay, so that's the moles of ions. Sodium plus chloride. We want the moles of sodium chloride in the solution. So we need to take this number and divide by 2. Because 1 mole of sodium chloride gives 2 moles of ions. So you can think about it, or you can do it like this. 1 mole sodium chloride equals 2 moles of ions. And you could use that as a conversion factor. So you've got your 0.0279296. That's moles of ions times 1 mole of sodium chloride per 2 moles of ions. Now you don't have to write it out, but this is one of those things, it's really easy to get it backwards. Sig figs on this is a pain. We'll just go with 3, 0.0136 moles of sodium chloride. Any questions?
So if you said we need to take into account the number of ions,
Yes.
in this exam, should we?
Well, this will not be on the exam this afternoon, but it could show up on the final exam or the homework.
So whenever we have a solute that can dissolve into
Ions. You have to take into account that it does form ions. And the reason is that the colligative properties that we're talking about depend on the number of particles. So a sodium ion is a particle, and a chloride ion is another particle. And when you've got factors of like 2 and 3 and 4, it has a big impact on the property. Did you have a question?
So when it's an ionic compound, at the end, which one the mole is just divided by how many there are? Once they dissociate?
Yeah, in this example where we're calculating the moles, then you divide by the number of ions in a formula unit. If you're doing the problem the other way, where maybe we're trying to calculate the solution here, then when you calculate the mole fraction, if you were given moles of sodium chloride, maybe it had 2 moles of sodium chloride, you'd have to multiply by 2. Any questions? If you think of it in terms of, if you write it out, okay, 1 mole of sodium chloride equals 2 moles of ions, and use that as a conversion factor, then you don't have to think about it so much. You can show it to yourself with units and be okay. Colligative properties are important in solutions used in medicine. So, you go to the hospital and you have to have a procedure done or something, and one of the first things they do is they stick an IV in your arm, right? And they're pumping who knows what into you. Well, it's really important what is in that bag of solution that they're hanging there. It needs to have the same molality as your blood, because you don't want it to draw water out of your tissues and you don't want it to push water into your tissues. So here's some micrographs of red blood cells. So normal red blood cells are supposed to look like this. They kind of look like little donuts on one side. They're round, and they've got this dip in the middle. This is if the blood cells are in an isotonic or isosmotic solution, where the osmotic pressure of the solution is the same as the osmotic pressure of the things that are inside the cell on the other side of that membrane. If you use an hyperosmotic or a hypotonic solution where the concentration is higher, the pressure, osmotic pressure is higher, it's going to pull water out of the red blood cells and cause them to shrivel up. It's called crenation when blood cells do that. They get all spiky. You can just kind of tell that's not going to be good, right? Hypoosmotic or hypotonic is when the solution has too little solute, a low osmotic pressure, and that drives water into the red blood cells. You look at these and you're like, well, they're a little bloated. That doesn't look so bad. It doesn't look as ugly as this. The thing is, if that goes on, the red blood cells will burst. That's bad. Okay? So the osmotic pressure of solutions used in IVs is really, really important. Any questions? So what they usually use is called isotonic saline. It's 0.9 grams of sodium chloride per 100 milliliters of solution, or as a percentage, it's 0.9% by it's mass to volume, actually. And the units that are used in medicine are related to the units that we've looked at, but a common one is instead of just mass percent or volume percent, they use a combination. It's percent mass to volume, the mass of solute over the volume of solution. And that's because solutes are typically weighed and solutions are liquids, and so it's easier to measure their volume. People have created all of these different units to be convenient for the situation in which they're used. Any questions?